Hello everyone, welcome to the second lecture of this module on tactile and force sensors. We are discussing the course on microsensors and nanosensors. In our first lecture of this tactile sensors, we have discussed about different type of tactile sensors, which include touch sensors, spatial sensors and slip sensors. We have seen that using touch sensor actually you can design spatial sensor as well as slip sensors. Spatial sensors is nothing but a coordinated touch sensor in the space. Okay. Similarly, we have seen the definition of a slip sensor. Okay. Then we have also seen that tactile sensors uses different modes of transduction like resistive or piezoresistive, then tunneling, capacitive, optical, ultrasonic, magnetic and piezoelectric. Okay. So, based on these transduction techniques, we have various tactile sensors. We have also seen their how they are implemented in very brief and what are their advantages and what are their specific applications, particularly the contact tactile sensors as well as non-contact tactile sensors, right. So, let us see brief fabrication process for these sensors to be fabricated. Okay. So, let us talk about very simple tactile sensors which are fabricated by making simply or patterning two different conducting layers. Okay. We will see that how the pull up resistors and other arrangements have been done to capture if something has been touched or not touched. If you remember in the definition of tactile sensors, we have discussed that we do not have to actually quantify the force. Of course, for some of the devices we have to be utilizing the threshold force or threshold pressure value, but usually we do not quantify this. So, if the force applied is less than the threshold voltage, we say no touch, and when the force applied is greater than the threshold voltage, okay, threshold force, we will see that the object has been touched. Okay. So, in line with this definition, let us see the fabrication of the simplest tactile sensors that exist. Okay. Although there are several methods that can be used to fabricate tactile sensor, but these method are are the most similar method. Okay. So, for most of the tactile sensor, a thin layer of material is required which is responsive to strain. Okay. So, mostly a material will be responding the strain. Mostly these materials are either piezoresistive materials or very thin layer of the resistive material itself, but having some flexibility and other things. Okay. A simple tactile sensor producing an on-off output can be formed with two layers of foil, okay, or two layers of thin film, okay, and a spacer. Okay. So, the spacer has generally rounded shapes, something like this. So, this is a typical tactile sensor. You can see that you have two layers of thin films, okay, or sometime it is also called foil. Okay. So, this is layer 1, or I am calling it top layer, and this is the bottom layer of the foil, okay, or the thin film, bottom layer. Okay. And then you have spacers in between, something like this. Okay. Usually the spacer have this shape, okay, but it is not a hard and fast rule to have this shape. It can be of different sizes. Okay. So, these films or foils are usually deposited or usually fabricated by MEMS process by etching the layers. Okay. And the top electrode is top layer is usually fabricated by some deposition techniques. We have discussed the deposition techniques in very brief, like we have there are various methods of deposition. You have PVD methods, which is known as physical vapor deposition, and you have a CVD, chemical vapor deposition. Mostly these techniques are used to make this top layer of this film, okay, of this setup, and the bottom layer is usually made by etching the MEMS or etching the silicon using the MEMS technology. Okay. In this configuration, one layer is always grounded. So, you see this, the top electrode or the top foil is grounded. Okay. The bottom foil is attached to a pull-up resistor. This is the configuration of just a layout of a pull-up resistor. Pull-up and pull-down resistors are used in analog and digital circuit to set a known default voltage level at a node. Okay, that is what we are doing in this configuration. Okay, a pull-up resistor connects the node to a higher voltage level, usually to the VCC value. Here this value I am using a plus 5 volt. You can have other values. Okay, so this connection ensure the node default to a logic high. Okay, when not actively driven. Okay. These resistors prevent floating inputs. You know that in digital circuits you have 3 outputs, either low, high or floating. So, these resistors prevent floating inputs which can cause say erratic or undefined behavior in the circuit. So, this is how the bottom layer is connected to pull-up resistor. So, this is the basic configuration. The top foil is grounded, bottom is connected to a pull-up resistor. Okay. Now, if more than one sensing region is needed, so what it means is, like here I am having this as a sensing region. Okay. If I have multiple regions, like for example, this is another region. So, if I am applying a force F1, there is a chance that there will be a force applied F2 here. Particularly if you talk about in term of tactile force sensors, we have seen the spatial sensors where you need to have multiple touch points. Okay. So, this is an example of that. So, if more than one sensing region is needed, usually along with this pull-up resistor, a multiplexer is employed. Okay. So, when an external force is applied to this upper conductor over the hole in this spacer, okay, this top leaf will flex. Okay. This top foil is going to flex. Okay. Now, when this force is sufficient to cross the threshold voltage or threshold force, okay, this leaf, the top leaf will touch this bottom foil. Okay. Now, when it touches this bottom foil, what it is doing is it is making a electrical contact with this. Okay. When it is connected, means both are at ground, means this pull-up resistor configuration is at ground. Okay. So, if it is at ground, means that this output is 0, right. So, this is kind of null deflection kind of a tactile sensor, means that when there was no force applied, there was certain output. Okay. When there is a force applied, the output voltage is 0. So, when the output says 0, means there is a force applied or something has been touched. So, it is a touch or not touch sensor. Okay. So, the criteria is being fulfilled. Okay. So, when there is output, means it is not touched, some say plus 5 volt, means that it is not being touched. When this output goes to 0, means it has been touched. All right. The upper and the lower conductive layers can be manufactured through screen printing of conductive inks. Okay. Usually, the substrate used for this printing is polypropylene, but then it can also be done on other substrates. Okay. So, multiple sensing locations can be created by printing conductive ink in row and column patterns. Okay. So, this screen printing was usually used in this bulky devices. Okay. where the feature size or this spacer gap, for example, is of size say around 200 micron. Okay. Please note that the gap between them are defining its sensitivity and other things. Okay, we will see that. Okay. Now, what you are doing is you can define multiple sensing locations by creating a row and column pattern. Okay, something like this. So, you have this spacer regions. Similarly, you can pattern like this. Okay. So, you can have multiple force points. So, for example, say these are spacer points, means force can be applied say this location, all these points are, all these points can be used as a touch points. Okay. So, the older generation devices, in fact, currently also some devices are fabricated using this screen printing technology, but nowadays modern printing technology are arising, particularly say inkjet printers. Then you have aerosol jet printers. You have plasma jet printers and so on. Okay. Depending on the complexity of the feature size as well as complexity of the structure, okay, you have multiple printing devices. It also depends on what kind of ink you are using. Say for example, in screen printing you need very high viscosity, while inkjet printer do not need very high viscosity. Okay. So, anything say 2 centipoise to say 20 centipoise is more than enough to print a metallic ink. Similarly, aerosol jet printer can even print below 2 centipoise, say anything say 0.4 centipoise or say 0.8 centipoise is this kind of viscosity is more than enough to be printed using aerosol jet printer, because their operations are different. But yeah, so it all depend on the complexity of the tactile sensor and the surfaces on which you are printing. Okay. So, a good tactile sensor can be constructed using piezoelectric films also, like the polymer PVDF, which is very popular piezoelectric material. Okay. This can be the advantage of this kind of devices is they can operate in both mode, either active mode or passive mode. Okay. Multiple transduction techniques can be coupled together to generate better results. So, you can have multiple transduction technique, like in the piezoelectric device you can also have capacitive transduction technique coupled. Okay. So that you can have multiple results. So, let us discuss one example where ultrasonic transduction technique and piezoelectric transduction techniques are coupled together. Okay. This will give you a overall idea that how multiple transduction techniques can be coupled in a same device to have more precise and more sensitive results. Okay. Let us consider this diagram where you have two PVDF films and in between you have a compressive film. Okay. Now, this oscillator is attached to the bottom PVDF film, and along with that you have this op-amp configuration, and then you are taking the output. We will see what all these components are. Okay. So, if you see, three films has been laminated. Okay. This is film 1 bottom, this is second film which is the compressive film, and this is the third film which is the top film. Okay. This film 1 and film 3 are the PVDF films. Okay. These three films has been laminated together. Okay. The upper film and the bottom film, as I have mentioned, are the PVDF film. The center film does the acoustic coupling between film 1 and film 3, or between the two PVDF film. That is why I am calling it a compressive film. Okay. The softness of this sensor is defined by all these three films. Okay. And in turn it defines the sensing parameter, for example, the sensitivity of this overall device, okay, the dynamic range of this device and other parameters. Okay. Now, since this PVDF is piezoelectric in nature, okay, AC voltage supplied from this oscillator coupled to this PVDF film. Okay. Now, since this is a piezoelectric material, okay, this PVDF means the excitation signal generates mechanical contraction in this film. Okay. It is, this oscillator is giving certain kind of AC pulses, okay, and accordingly you have mechanical deformation in this bottom electrode or bottom PVDF film. Okay. These contraction transmit through this compressive film. Okay. So, compressive film, what it does, it transfer this mechanical vibration exactly to the top PVDF film. Okay. Now, since this layer 3 is also a piezoelectric layer, it acts as a receiver. Okay. Please recall that this piezoelectric phenomena is reversible in nature. Okay. So, what you are transferring, that oscillator is making certain mechanical deformation in the first film. This mechanical deformation is transferred to film 3 via this second film, which is a compressive film. Okay. Now, the mechanical structure changes are there in film 3 because it is also a piezoelectric material, and since this piezoelectric behavior is reversible, the upper film produces a alternating voltage, and this AC voltage is with respect to the mechanical vibration from this compressive film. Okay. These oscillations are amplified, and then this is supplied to a demodulator which is synchronous in nature. Okay. The demodulator responds to both the amplitude and phase variation of the received signal. Okay. Now, after applying this compressive force F to the top film, the mechanical coupling within the 3-layer assembly is altered. So, initially you have certain output, and when you are applying this force, there is a deformation, mechanical deformation. Okay. And because of that, the mechanical coupling in these 3 films will change. Okay. Because of this change, it will influence both the amplitude and phase of the received signal at this output. Okay. The demodulator detects this variation and converts them into a variable voltage output, which can be a signature of the applied force. Okay. So, in this example, you have seen that the ultrasonic principle is coupled to this piezoelectric behavior. Okay. What you are doing is, you are providing a oscillation. Okay. Because of this, there is a mechanical deformation which is transferred to this compressive film, and which in turn is, changing the behavior of this piezoelectric top layer of PVDF. Okay. And there was a voltage established. Okay. When you apply this force, it alters this chain. Okay. And at the same time, the output voltage is modulated. Okay. Based on that, you can actually predict the applied force. Okay. Now, this is a simple structures. It can be fabricated by making or depositing this PVDF film on some substrate. You can also deposit this compressive film, and I mean, usually these structures are bulky in nature. If you see, okay, you have advanced techniques of fabrication of this piezoelectric tactile sensors, which are usually MEMS based. Okay. So, it is done by etching the silicon layer in a wafer. Okay. And have the subsequent layers. Usually those devices are based on either piezoresistive phenomena or are usually based on say piezoelectric phenomena. Okay. And we have also seen that there are various techniques available, particularly at the printing side, to generate these devices. These printing techniques include screen printing, inkjet printing, aerosol jet printing, and so on. Okay. Now, since we now understand the fabrication process of this piezoelectric or other kind of devices, let us see what are the limitations of tactile sensors. Okay. Please note that in all these devices there is a trade off between sensitivity and durability. Okay. So, if you target the durability, you have to compromise at the sensitivity. Okay. However, there are certain devices like the optical devices where these things can be taken care by the lens system and other things. Okay. Then integration of this tactile sensors with control systems is somehow challenging. Okay. Then these devices are very difficult to calibrate. Okay. And of course, it is very complex to calibrate it, particularly because of the association of the threshold force. Okay. Because of that, it becomes very complex to calibrate it. Okay. Also, whatever we are talking is mostly the normal force, but then there are other kind of forces that can be exerted. Okay. And that is why this calibration is even more complex. So, when you talk about shear forces and others, it becomes even more complex. Okay. Then the ambient interferences from humidity and temperature conditions in the ambient is one of the major challenges for this tactile sensors. Okay. So, with this I hope that we have gained some understanding of the tactile sensors. We have seen different kind of tactile sensors and we have also seen their fabrication process. We have seen that touch tactile sensor, spatial tactile sensor and slip tactile sensors can be fabricated by either by MEMS technology or by different printing techniques. Some of the example we have seen. We have also seen that two or more than two transduction techniques can be coupled together to generate better sensitivity and to have a higher dynamic range. In case of ultrasonic and piezoelectric device, we have seen that. Okay. So, that is all about tactile sensor. In the next class, we will discuss about pressure sensors. Thank you.